welcome. We're talking chapter 2, I think. So talking chapter 2, last time we were talking about measurements, how to properly take measurements. We also talked about significant figures and calculations. So a couple of reminders on both of those things that we talked about. Obviously, when you do take a measurement, it is always important to look at the scale that you are dealing with and barely, there you go. Look at really, as we talked about, the two sort of markings. And again, there's usually a larger marking and there's usually a smaller marking. So in this example there, larger sort of marking or big marking is a 10 milliliters. If I drew the right amount of lines there between those two, there should be 10 lines. Remember, we do really start counting here and then end at the next big line there. And that means that each of the small markings here would be 1 milliliter. And as we talked about, not in 100% of the time, but in most cases, you could take the reading to one more place to the right of the smallest marking is typically what you're able to do. So, if we had something in this area, that would be 11, that would be 12, that would be 13, that would be 14, that would be 15. So perhaps you record something like 14.7 milliliters. Again, we always want to record all those certain numbers. We also want to record really where sort of the uncertainty comes in this measurement, which is that first, again, sometimes referred to as estimated digit or first uncertain digit. And this again would encompass what is significant figures. So again, all these guys here would have 3 significant figures where the uncertainty would lie in that last significant figure. So that was something we talked about too last time. Sometimes people get in the habit of thinking it is always the last number that is written is where the estimation or uncertainty lies. And that's not always the case. It is, and a lot of times it is the case. But it really is where the last significant figure is in the number is where the uncertainty lies. So years ago in your lab, this was like one of the questions, like again, 12,000, something like that. And again, the way that's written, if that was a measurement, it should only have how many significant figures? 2. And the uncertainty here actually should lie in the 2. Again, not at the 0 at the end. And although, like I said, in a lot of cases, it is that last number, but it's not always going to be that last number. So definitely always the last significant figure. We talked about counting significant figures, obviously correctly. Anything that's a non-zero is obviously going to be significant. When it comes to zeros, any zeros that come before the very first non-zero number are not going to be significant. Any zeros that are trapped between 2 non-zero numbers will be significant. And any zeros at the end of a number will only be significant if there is a decimal point somewhere in that number. Again, the decimal point does not need to be right next to those zeros, but it just needs to be somewhere in that number. Also remember that if you write a number in scientific notation, all the numbers that come before the times 10 part, all these numbers, those numbers are always significant. So again, there may be a situation where you need to give an answer to the proper number of significant figures, and you really can't do that in decimal form. So one way that you could always do that is write it in scientific notation, because you could frankly control how many significant figures you got going on there by writing it correctly there. We finished up, I think, as well, talking about significant figures and calculations. So once again, the two kind of common groups of calculations that we do is multiply or divide. And when we multiply and divide, what we're looking at is the number of significant figures there are. And we're always looking for the least number of significant figures. So whatever you're multiplying or whatever you're dividing, whichever number has the least number of significant figures should be how many significant figures your answer should end up with. Now, when we add and subtract, we're actually looking at decimal places. We're not looking at significant figures, and it does go the same way. We are looking at the least number of decimal places. So again, whatever numbers you're adding or subtracting, whichever one has the least number of decimal places is how many decimal places your answer should have. Remember, though, that is just how many decimal places. Your answer may have a different number of significant figures. which is important if you continue on with the calculation or continue on with that number to do another calculation. That would be really important. If we have, or if we're adding numbers that there is no decimal place, for example, like 11 plus 1.11, I'm going with all ones today. There we go, 2 and 1 there. Where should I go? The smallest number of decimal places is this guy that has none. Yes, that is like your worst measurement. So you would actually take it to 12, yes, and drop the rest of them. So that comes up occasionally. Any questions on any of that stuff there that we talked about? Okay, I think I kind of jumped the gun on some of that. So we'll go through some of these slides that you have that cover some of the sig fig stuff just to make sure. Once again, this is a table that tells us like what we were talking about in terms of zeros and significant sort of figures. 4.5 would definitely have 2 significant figures. All these guys are non-zeros, so they would all be significant. And my numbers kind of moved around here, so we'll go with 3 on that. I'll just go with the ones I could see. That would be 4 on that particular one there. Again, the zeros at the end are going to be significant. Not sure what number was there, but it had 4 significant figures apparently. All right. So looking at these, all non-zeros, once again, are going to be significant. So every single one that we see here would be significant in each of these guys. Remember that when we are sort of counting significant figures, we always want to go left to right and start counting as soon as we hit the very first non-zero number. These are zeros, again, that are sort of between non-zero numbers, and they're always going to be significant. So because we would start left to right, we would start counting there. These couple of zeros would obviously then be significant in this case. And obviously the 8 at the end would be significant. So there we got our 4. And in all these cases, we would start counting here, significant and significant. On this one, obviously these zeros come before, so they are not significant. Even that 0 that's after the decimal point is not significant, because technically speaking, we do not start counting until we hit the 7. So it's at that 7 where we start counting, and now that 0 is trapped between 2 non-zeros, and that 2 at the end would be significant. So again, that is why it is 3. So it's very common. Sometimes people have questions like, hey, you know, I got these zeros, they come after the decimal point, you know, shouldn't they be significant? And the answer again is what I just said. We really don't start counting until we hit that very first one. So they are still considered leading zeros at that point, even though again, that they may follow the decimal point and stuff like that. This 0 at this end, should it be significant? It should be, again, because of that decimal point. So this particular gun, we would start counting there. This would be significant, significant, significant. And that guy, again, would have 4 significant figures in that particular case. Any questions on that there? And again, same thing here. We start counting there, and basically everybody there is going to be significant. All of our zeros are basically trapped. Here's our non-decimal decimal situation for those guys come at the end. So once again, this guy has no decimal point written. So even though we sometimes assume it's at the end, in this case, because it's not written, we're not going to assume it in case of significant figures. That means in this case, it is the 2 here. That is our 1 significant figure. And in this case, the uncertain number would be the 2 in this case, right? So the 2 is our certain and our uncertain number, really. It's really our uncertain number. And again, what that means is it's not the greatest measurement. You got a lot of error there. It could be 200, could be 300, could be 100. That's a big span of maybe-ish in terms of that type of measurement. In this case, all these zeros here, once again, are going to be significant. They are at the end of the number. We've already started counting because we hit the 4. And again, we have the decimal point there, so they would all be significant. Any questions on that there? And again, a few more examples of these zeros. So starting to count here, 0 at the end, significant because of the decimal. These zeros are not significant because we have not started counting until we got to the 2. And that would be the 2 significant figures. Once again, all these zeros would not be significant. And we would start counting there at the 3, which would give us 1 significant figure. A reminder again that if you were to take a number, for example, like this, 0.440, and you did want to write it in scientific notation, when you turn that into scientific notation, We would need to go one more place to the right. That would be 4.40 times 10 to the minus 1. The number of significant figures is 3. Number of significant figures, the way I wrote it here, is 3 as well. Yeah, so all those would be 3. So you do not want to lose significant figures if you change it from decimal to scientific notation, or the other way around if you change it from scientific notation to decimal. So this would not be good. Why? How many significant figures does this number have? It has only 2 significant figures, but our original number had 3. So again, it's important not to lop off those numbers. And it sometimes happens when people go, again, back and forth from scientific notation to decimal, or, going the opposite way. Any questions on that there? And again, these would all be examples where those zeros at the end are not going to be significant. Once again, there is no decimal point written, so all those zeros will not be significant in each of these cases, which means, once again, these would be the 2 significant figures, with the uncertain digit being that guy. This would be the 2 uncertain numbers, although I over scribbled there, so we'll circle it. And that 1 that I totally erased there by scribbling on it would be our uncertain number. These would be the 3 significant figures, with the 5 being the uncertain or estimated digit in each of those cases. And again, as we talked about, scientific notation, a really good way to, kind of control the number of significant figures that you need. As I mentioned earlier, when we were talking about scientific notation, once again, you do not necessarily have to write every number in scientific notation or anything like that. I know somebody used to teach and made everybody write every single number in scientific notation, unless obviously the instructions say to do so. But again, as I mentioned, you may have to in certain situations to get to the right number of significant figures. In each of these cases, we now have our 3 significant figures, because there now is a decimal. And because that has 3 significant figures, once again, in scientific notation, it is recognized as having 3 significant figures. This has our 1 significant figure, which is why when we go into scientific notation, we pretty much drop all those zeros, because if we included it, they would all then become significant. And now we have just went from 1 significant figure to a lot of significant figures, which is clearly not what our original number was, right? Our original number is a pretty crappy measurement, right? It's like all the errors way over there in the hundredth, right? So we don't want to add it and change really that. All right, so take a second here, identify the significant and non-significant zeros in each of the following and write them in correct scientific notation. All right, let's take a look. So first off, how many significant figures total would this number have? It does have 4. We would start counting here. The 0 at the end, again, would be significant because there is a decimal point there. So it would have total of 4 significant figures, with, obviously, to answer the question, the 0 at the end is significant. The zeros at the beginning are not. To turn this into scientific notation, that would give me a 2.650 as we go 1, 2, 3 places to the right, times 10 to the minus 3. Once again, we do want to keep the 0 there as we go scientific notation to keep the 4 significant figures alive. Any questions on that one there? Looking at this one, this number here for B would have how many total significant figures? This one would have 5 significant figures. So once again, we would start counting here at the 4. The 3 is significant. This 0 is between 2 non-zeros, so it does make it significant, and the rest of them would be significant as well. So the only 0 here is going to be significant in this particular number. To get us this proper scientific notation, we got to roll to the left there. So that's going to be 4.3026 times 10 to the 1. This, once again, now has 5 significant figures, and this guy had 5 significant figures. So once again, we're not going to lose any significant figures along the way when we transfer it over. How about the last one? How many total significant figures we got going on there? It is 4. Once again, we would start counting here. That's going to be significant since it's trapped. The 2 4s are significant. The 3 zeros are not going to be significant because there's no decimal point written in that case. So that would get us something. We would go 1, 2, 3, 4, 5, 6 places to the left, it looks like. So that's going to give us 1.044 times 10 to the 6. I should be a good chemist there and put units on all of these, I suppose, so they don't take away my license if I had one. I really don't have one, but if I did, they would take it away. That is 4 significant figures there to match the 4 significant figures here. So once again, this example, we would actually want to drop the zeros off of our scientific notation. Otherwise, if we put them in there, we would end up with 2, 4, 6, 7 significant figures, which is clearly more than our original numbers should have. Any questions on that there? Yes. How did I get the the 6? Yeah, so we had this number originally, unless I miscounted, which could happen. So although there's no decimal point written, in the case of turning it into scientific notation, we do assume that the decimal point would end up here at the end of the number. So we got to go 1 place, right? 2 places, 3 places, 4 places, 5 places. If we stop right there, that's 10.44. Remember, it's got to be a number between 1 and 10. So we got to go 1 more place, and that gives us the 1.04. So it's the 6 places. It's positive 6 because it's a large number, right? And when we have to move it to the left, basically it's going to be a positive exponent. Or if you want to think about it as a positive number, a large number will be a positive exponent. Other questions on that? Yeah. Yeah. I got the one, the same deal. We got 43.026. So once again, scientific notation, the first number, which is really important, has to be a number between 1 and 10. Can't be 10, can't be less than 1. It's got to be in there. So if I just stopped at this point where the decimal point started, it's 43, which is clearly not a number between 1 and 10. If I went to the right, I would end up with 430, which is clearly not between 1 and 10. My only option to get between 1 and 10 is to go to the left 1 spot, and that will give us the 4.3 number, which is obviously between 1 and 10. And obviously the 1 is how many places I had to move to get there. Yeah. And again, in this case, this is a large number, basically above 1, so it should be a positive exponent. Other questions on that? Got it. Hopefully they agree. All right. There we go. All right. I think we also talked about this, but just to make sure, there's really 2 types of numbers that we come across in chemistry and in most cases. One is actually a measured number where you actually do some type of measurement, and that's really where significant figures sort of come into play. The other type of number is what is considered an exact number, and an exact number is really found one of 2 ways. It can either be something that is counted. So the classic example is you got a basket of 8 apples or something like that. So if you had a basket of apples, you want to know how many apples there were, you would frankly just go count them. You're not going to design an experiment to figure out how many apples are sitting in the bucket, right? So that's a common way we get it. The other common way is through equalities, and these are equalities, or sometimes referred to as definitions. And what an equality is basically 2 different values that are on different units, but represent the same amount of something. So when we talk about something is 12 inches, that's really the same length, right, as it being 1 foot. If you had 100 pennies, that's the same amount of money as if you had $1, right? So those things are equivalent to each other, and they're referred to as equalities. The deal with exact numbers is pretty much this. Because they are exact numbers, you pretty much could have unlimited number of significant figures you could apply to it. So you could say it has 4, I could say it has 3, somebody else could say it has 400, because they're basically exact numbers. Where exact numbers really come into effect is what we're going to talk about here in just a bit, is when we do calculations. And when we do calculations and we want to get the proper number of significant figures at the end of our calculation, if we come across something that's considered a exact number, which is pretty much a conversion factor like these equalities here, we basically ignore them because everybody could look at it and go give it different numbers of significant figures. So we sort of ignore exact numbers and calculations. And what that usually means, as we will see, is we're usually left with a lot of times the original number we were doing the calculation from as to how many significant figures we should have. Now, there is sort of an exception where we would look at an exact number for doing some type of calculation. And that exception has to do with really the different types of units. So we talked, I think, at the beginning that there really are like English sort of units, right, that we use, and then pretty much everybody else is rolling metric, right? And if you have some type of conversion factor or equality that is a English to English sort of equality or conversion factor, that 100% is going to be an exact number, like this guy right here. That's an English to English sort of conversion. If you have some type of metric to metric conversion, that also is going to be considered an exact number, which would be like this guy here. 1 kilogram is 1,000 grams, would be a metric to metric conversion. Now, typically speaking, the only time when you do a calculation that you should consider an equality or conversion factor that comes from an equality is if you kind of cross over metric to English or vice versa. Like 1 quart is 900 and, going off the top of my head, 46 milliliters, or it could be 64, one of those, but we'll go with this one here. And this technically will be sort of a crossover from English units to metric units. And we would want to look at the significant figures in this part of the number, not the one that's 1. So there'll always be an inequality. 1 of something is equal to a number, basically, and you would want to look at the number part. So that's the one place where, technically speaking, you should look at it. There are a couple of exceptions, and one exception would be like 1 inch is exactly 2.54 centimeters. That is considered an exact measurement. In addition, some people do 453.6 grams as a pound is an exact one, but typically speaking, if you cross over metric to English or English to metric, you really should look at the significant figures. So all these sort of numbers here would be considered exact numbers, as they are, once again, metric to metric, metric to metric, metric to metric, English to English, English to English sort of conversion. So really the take home for exact numbers, and really where it comes up most of the time, is when we're doing some type of conversion type problem and we're using these sort of equalities as conversion factors. The nice thing about it, it comes up and you pretty much can ignore it. You don't have to worry about it in most cases. Now, even when you do have to worry about something like an English to metric sort of conversion, and you should look at it, I'm going to tell you the right chemistry thing is you should look at it. I'll tell you, probably more times than not, you could probably ignore it too, and you'll still be okay if you kind of go with the first number. So a lot of times in a conversion problem, that first number is pretty darn close, if not correct number of significant figures your answer should have, if all you're doing is simply kind of converting it. But you should look at what you're using in the problem to do it correctly. All right, so we want to identify these numbers as either being measured or exact, and give the number of significant figures in each measured. Is 3 coins measured or exact? Probably be something you would count, right? So that would probably be an exact number. Diameter of a circle would be 7.902. That would be measured. And how many sig figs would that have? Does have 4 sig figs. All of those guys are significant. 60 minutes is equal to 1 hour. That is an exact. That is something you should know, right? Yes. Seconds in an hour. That's not second an hour. It's 3,600. Yes. Seconds in a minute. 60. Yeah. Got a little quiet. I'm getting a little nervous here to ask the next question. Hours in a day? 24. Don't put 60. Yeah. People do that all the time. Like, hey, they do a conversion where they got like 60 seconds to a minute, 60 minutes in an hour, 60 hours in a day. So don't do that. Right? So there's only 24. That's plenty. Yeah. It will not. So if it's an exact number, it won't affect the significant figures in your answer if you're doing a calculation that involves those. Technically speaking, if it is an exact number, it really could have as many significant figures as you want. So there's like an unlimited number of sig figs. And that's really why we sort of throw them out when we're doing calculations, because everybody would look at it differently, right? So I would say maybe there's 4 in that number, you might say there's 2, and we would end up with different answers at the end of our calculation. So that's why we really kind of throw those out in a sense, and not worry about them when we are doing calculations. Other questions? All right, they hopefully agree, so that's good. All right. All right, so let's just roll through these here. Sig figs, first one is, it is 2. That would be these. Next one, 4. This one here, see? 1, which would be that one. And lastly, 3, which would be all 3 of them, yeah? All right. They agree, that's good. All right. All right, we'll roll through these two. A, which one has 3 significant figures? It is 2, right? This one's got 4, this one's got 4, this one's got 3. Where all the zeros are significant. I heard 3 and I heard 2. I did not hear 1, which is good. Yes. Are all the zeros significant here? They are. There's a decimal, so these are significant. Are all the zeros significant here? They are, because it's written in scientific notation. So 2 and 3 are correct, actually, in this case, right? Any questions on that one? No? And lastly, the number of significant figures in this number is, it is 3. Once again, all those numbers before the times 10 part are going to be significant. Any questions on any of those there? Yeah, they agree. That's good. All right. So we talked about this. So I'm just gonna kind of throw through this. This is what we talked about the other day. Again, also we talked about, I think, not to do any super rounding, right, or extreme rounding. So make sure you do round. Again, proper rules like normal. We're going 5 and above. We're going to round up if the number next to where we need to end is 5 or above. If the number next to where we end is less than that, then we just drop off those numbers. And remember that if we're doing multiple parts of a calculation, you really kind of want to wait to the end to sort of round. You do want to kind of keep track of everything along the way in your calculation, but it's really good procedure to wait to the end there to round. So we won't go through these too much here, but again, if we wanted to take this guy to 3 sig figs, that would be the 2. So we would look at the 3. So definitely we would drop it. If we wanted to go to 2 sig figs, that would be the 4. So that would be the 2. So we would drop the rest of the numbers. And very similar here, we would go to the 7 for 3 sig figs. We would round up. And to go to 2 sig figs, we would go to the 4 and look at the 7 and also round up if we wanted to end up with 2 sig figs and so forth there at the end. If we wanted 3 sig figs on this guy here, we would go to the 5 and look at the 6. So we would round up. Once again, here we would want to go 3, 2, 6, 0, no decimal, right? Otherwise, we would have 4 significant figures. Or absolutely, you could do a little scientific notation action there, right? And you could write it in scientific notation. If we want to go to 2, we would look at the second number there, which is a 2. We would look at the 5, and once again, we would do one of 2 things. We would write 3,300. Again, once again, no decimal. Otherwise, we got too many sig figs. Or we could do our scientific notation, which has 2 significant figures as well. All right. We want to round this to 3 sig figs. What should my answer be? 3.15. 3 sig figs would be here. This would tell us we should round up. We should also lay up some units there, right? 2 sig figs, the answer would be 3.1. Once again, we would go to the 1. We would look at the 4. And in this case, we would just drop the rest of the numbers. And again, probably should include the units. Any questions on that one there? All right. All right, so take a second and write each of these in 3 significant figures. Why don't you also put... All right, let's take a look. So we're going 3 sig figs here. So on the first one, that should take us there. And we should end up with 825 on the rounding up on that. Scientific notation properly for 3 sig figs would look something like this. Yes. So once again, we would go 1, 2 places there to the left to put it into scientific notation. Any questions on that one there? 3 sig figs here takes us to the 2. What do we do with the rest of the numbers? We should drop them. So we're going to go with 0.112 grams. To get us to scientific notation, we actually need to go 1 place to the right there. That's going to give us 1.12 times 10 to the minus 1 grams, right? Any questions on that one there? By the way, we might have mentioned this, but just in case, it really is important that if you do have sort of a decimal number such as that there, that you do put the 0 there. Again, especially if you have a lot of decimals and you're doing calculations. Sometimes numbers do run into each other, so it really is proper to kind of put the 0 there in front of the decimal. Again, just to really separate out the numbers and stuff like that. Lastly, here we want 3 sig figs. How do we get that? You gotta add a 0. You add a 0. That would be 3 significant figures. But probably the best way would have been maybe a little scientific notation action, right? Where we could add that 0. In this case, we would go nowhere, right? So we can't really do that. We would go 0, which is nothing. So this probably would be the best way to do it, would be that one there on the left. Question on that there? All right, there we go. All right, so again, we talked about this, so I'm just going to kind of scroll through this. Smallest number of sig figs, like we talked about at the beginning. So once again, here 3 divided by 3 should give us 3 significant figures. This also is a reminder, and I think we might have mentioned it, your calculators do not spit out your answer in the right number of sig figs, right? So you do need to do a little bit of editing when you are using your calculator. And in this case, you might need to add some zeros there to get you the right number of sig figs, or you might need to take off some numbers to get you to the right sig figs. Once again, if we're doing multiple steps like we talked about, we're going to be multiplying. So that would be 3 sig figs and 4 sig figs, which means technically speaking, the top number should have 3 significant figures, which would be divided by the bottom number that has 2 significant figures, which means really we should end up again with 2 significant figures. So you really do want to kind of keep track of everything along the way and make sure that you do end up with 2 significant figures, which again is what they ended up with right there. Why is it, say again? Why is it cubic centimeters? That's a good question. Let me see why they put cubic centimeters there. It really shouldn't be cubic centimeters. You're correct. In this calculation, if we multiply the top, that would actually give us square centimeters, right? And then we would be dividing by centimeters, which means technically speaking, the book is incorrect and it should be just centimeters in this case at that point. Yeah. So yeah, so we do want to watch the units. It definitely unit wise will cancel and reduce down the same way as obviously numbers will. But in this case, based on what I see here, it should end up as just centimeters at the end. Yeah. Other questions? See, sometimes the book is not right either, right? All right, so adding and subtracting, as we talked about as well, we're looking again at decimal places. So we got 3, 2, and 1. So once again, when it's all said and done, we do want to reduce it down to 1 decimal place. And again, a reminder that that does have 3 significant figures. If you should be taking it off into another calculation where you might need to look at significant figures. Same thing with subtracting. So once again here, the smallest number of decimal places would be the first one. So we would end up with 62.1, which has 1 decimal place, 3 significant figures. I might have mentioned it last time, but the real reason why we go kind of the least sig fig and the least number of decimal places is really your calculation is only as good as your worst measurement. And your worst measurement is really the one that limits how accurate or precise your sort of a measurement will be. So it's kind of like, you know, the weakest link kind of analogy, and it's the same thing here. So we should end up with how many decimal places here? we should end up with 1 decimal place, right? And again, provided they did the math right there, that should be 104.4, which once again does have 4 significant figures in this particular case. So again, on your calculator, you got to do a little bit of editing there to get yourself to the right answer. All right, any questions on sig figs, calculations, those type of things? Okay, we're going to sort of switch over and talk a little bit about doing actual, maybe some calculations, some conversion factors, some equalities, and prefixes. So prefixes are used in the metric system really to change the meaning. So like kilo, for example, is 10 to the 3, which is basically 1 times 10 to the 3. Centi, 10 to the minus 2, and so forth. Equalities, as we talked about a second ago, equalities are again 2 values that are on different units, but again, does represent the same amount of a substance that it may be. So here's a couple of metric equalities. 1 kilometer is 1,000 meters. 1 millimeter is 0.001 meters. Now, any equality that you come across, as we will talk about, you could write basically conversion factors for to use in calculation. And conversion factors are really nothing more than fractions. So for example, we could say that 1 kilometer over 1,000 meters would be one conversion factor we could use. Or we could use 1,000 meters over 1 kilometer. So these are really 2 sort of conversion factors that we could use from this particular equality. And we could use it in a calculation, as we will see in a few slides down the road here, but we could use it in a calculation, which is sometimes referred to as dimensional analysis. And that is essentially how you're supposed to sort of do conversion problems. So for example, let's just say we had 425 meters, and we want to know how many kilometers that would be. So we could do really a conversion problem here using our conversion factor that comes from our equality. And the way that we want to do it in chemistry is to really show the units canceling and set it up in a way where you can kind of see everything cancel. The nice thing about sort of fractions, which is really the basis sort of this approach, is opposites cancel. So if the unit you don't want is up on top, you need to put the same unit on the bottom, and vice versa. If the unit you don't want is on the bottom, you need to put the same unit up on top. It's basically the idea of the units will cancel just like if you divided 2 numbers that were exactly the same. So if you had like 2 divided by 2, that equals 1. If you had, say, centimeters up on top in terms of units and centimeters on the bottom, kind of like we were just looking at with that other problem there, they also will basically cancel each other out and equal 1. So units can sort of cancel out each other just like basically numbers can. So if we were to do this, we would start with our number that was given to us, which is 425 meters. Although it is technically not written as a fraction, when you write a number by itself and you were to turn it into a fraction, is that number up on top of the fraction or on the bottom of the fraction? On the top, right? And it's basically 425 over 1. So why that's important in this type of calculation is I could hopefully clearly see that my meters are up on top or on the bottom. The meters are on the top. Yeah, that's the meters right there. Meters are up on top. Yeah, 1's on the bottom. So because the meters are on top and I want to get rid of meters, I need to put meters in the opposite location, which means which conversion factor would put meters in the opposite location? The very first one, right? We could clearly see that the meters are on the bottom, right? And the kilometers, which is actually what we're looking for, are up on top. So we set this up people call it like railroad ties or something like that, but I like to just do parentheses and stuff. I'm going to use my conversion factor, which is 1,000 meters on the bottom, 1 kilometer on top. Now, what we are really doing here, mathematically speaking, is whatever's up on top, we are multiplying. So we're multiplying whatever's on the top, and we're going to come back, and whatever's on the bottom, we're going to divide. So everything on top gets multiplied, then you come back and divide by whatever numbers are on the bottom, which means in this case, basically I would take 425. I'm going to do that with my calculator here, hopefully. Take 425, and if you want, you can multiply it by 1. It's not going to really change the number unless you do what I did and hit 4. Try 1 there. There we go. And we end up with obviously 425 on top. That's upside down. Let me turn that around. There we go. 425 up on top. Now, I personally would hit equals at this point, you know, even if we had a real number up there. Then we want to come back and really divide by what's on the bottom. We don't really need to divide it by 1 because it's not going to change, but we do want to divide it by 1,000 here. If I could hold on to my calculator and put the right number of zeros on there. That is going to give me 0.425 in terms of my answer. Now, in terms of units, what we have going is, because we have meters on top and we have meters on the bottom, we essentially divided meters divided by meters, which means they cancel out. The unit that we are looking for is still on top, which means that unit comes over here, and we have now just did our conversion, and we know that there is 0.425 kilometers and 425 meters. First off, any question on sort of that setup there? We're going to see a few more examples as we go through some more slides here, but let's talk significant figures. And we were just talking about exact numbers, right? When we look at this calculation, there's really 2 things we're doing. We're multiplying and we're dividing, which is pretty much all you're going to do when you're doing any type of conversion problem where you're using conversion factors. You're just going to multiply and divide things. So when we multiply and divide, we should look at significant figures or decimal places. Sig figs, right? So whenever you do any sort of dimensional analysis problem like this, you should be looking at sig figs, and we want the lowest number of sig figs. When we look at that equality in the middle here that we used, that is a metric to metric equality, right? That would be considered what type of number? That would be considered an exact number. So this is what I was talking about a little bit ago. In this calculation, we frankly don't have to worry at all about what's going on with those numbers in terms of significant figures because they're an exact number. That means really in this problem, there is only one number that we should be concerned with, which was our original number, right? And our original number has how many significant figures? 3, which means our answer should end up with 3, which it did, yes? So a lot of times, like I was talking about earlier, when you're doing nothing more than using conversion factors to do these type of calculations, a lot of times that original number is probably the right number of significant figures that your answer should have. Again, with a little asterisk of it's not 100% foolproof. There are times when it is not the right number, but more times than not, probably it's going to be either the right number or pretty darn close to the right number of significant figures. Any questions on that there? So let's take a look at a few more sort of equalities here. And again, for each of these, we obviously can write conversion factors. The kilo prefix here, it really doesn't matter what unit you're talking about. So what I mean by that is 1 kilometer is 1,000 meters. 1 kiloliter would also be 1,000 liters. 1 kilogram would be 1,000 grams. So the base unit really doesn't matter when you're doing it. You could apply it to any unit the prefix sort of relationship of, in this case, 1 to 1,000 basically is always the same, regardless if you're talking about liters or meters or grams, when you look at it. Now, this is a table of some prefixes and ways to use it. And we do come across a lot of these here. And a lot of times people will see this sort of value given for each of these things. And we want to make sure that we actually do these guys correctly. And it's a very, very common error that people make, that they actually do these things sort of backwards. So let's talk about this one here, the kilo. So when we look at a table like this, it says kilo is 10 to the 3. And once again, if you needed to punch that in your calculator, basically you'd punch it in proper scientific notation as 1 times 10 to the 3, like we talked about using your exponent button to do that. When we look at these numbers here, or really even these numbers here, that is how much there is in the base unit to one of the prefix units. So this is how much there is in the base unit to one prefix unit. And it is very common that people do it backwards. So what does that mean? It means that if I had 1 kilogram, that would be the prefix unit, right? Kilogram. The base unit here would be grams. Yeah. I would have 10 to the 3 grams. I would not have 10 to the 3 kilograms in 1 gram, which is a very common way people do it wrong, backwards. So whatever numbers you see here is how much there is in the base unit to one of the prefix units. And it's, again, like I said, super common. People always flip them around. And like we saw on the previous page, if I had 1 kilometer, that would be 10 to the 3 meters. The conversion works the same way. By the way, 1 times 10 to the 3 is how much? 1,000. Yes, that's why we saw on the previous page, 1 kilometer is 1,000 meters. So that's just decimal form, if you will. Then here's some more that are common. So centi, for example, right? You do this one. I got centimeters and I got meters. You write it correctly, and then we'll see if you did. All right, what should go in front of the centimeters? What number? So when I look at this number here, that is how much there is in the base unit, which meters would be the base unit here. So the 10 to the minus 2 should go here, and this should be 1 centimeter here, not the other way around. Again, very common. People always go the other way around. I heard 100, which is a conversion that you could do by dividing 10 to the minus 2 to both sides. If you take 1 divided by 10 to the minus 2, you get that there is 100 centimeters in 1 meter. So that's the same relationship, and you get that by dividing this to the other side. So you could use either one. Was there a question? Yeah. Well, for example, it's very common that people will write something like this, that there's 10 to the minus 2 centimeters in 1 meter. That's the wrong way. Yeah. They think when they see these numbers, that's how much there is in the prefix unit to one of the regular base units. And it's a very common mistake. So it is not that way. And it's very common. A lot of times people even do it like this. For example, they'll go, oh, it's centi is like 100. So there's 100 meters is 1 centimeter. And again, they would do it backwards and stuff like that. So it's very common. People will do it backwards. Other questions on that? So if we had nano, which is 10 to the minus 9, that would mean that I would have in 1 nanometer 10 to the minus 9 meters, right? So let's say I wanted to do, let's say I had a number like 6.49 times 10 to the minus 7 meters. And I wanted to know how many nanometers that would be. Why don't you give it a go? See what you come up with. Set it up so you can see the units and see what you end up with. Let's take a look. So in this case, we would use our proper equality here. And again, we could write basically two conversion factors. We could say 1 nanometer over 10 to the minus 9 meters, or 10 to the minus 9 meters over 1 nanometer. Once again, that basically is 1 times 10 to the minus 9, if you need to kind of put that into your calculator. So we could do this sort of dimensional analysis way and set it up with our units. We would start with, we're starting on this side, 6.49 times 10 to the minus 7 meters. We're going to use our conversion factor, and which one will help us do that? The one on the left or the one on the right? So again, meters is technically on the top or bottom? Is on the top, which means meters needs to go on the bottom, right? Opposite to cancel, because we do want to end up with nanometers. So I'll go back here where maybe I got a little bit more room to write it. So we had 6.49 times 10 to the minus 7 meters. Using our conversion factor there, which I think was on the left, we would do our 10 to the minus 9 meters is 1 nanometer. The meters here would be divided out and cancel, and that will leave us nanometers. Once again, we're going to basically multiply what's on top. So 6.49 exponent button, -7. We're really multiplying it by 1, so you don't really need to do that. But if you like, you can multiply it by 1. We are then going to divide it by basically 1 times 10 to the minus 9, put in correctly in your calculator. And what you should end up with there is 649 nanometers. Yeah. Once again, this would be an exact number, so we don't have to worry about anything happening there in terms of significant figures. We would worry about this number, which has how many sig figs? 3. And our answer ends up with 3 as well. So again, significant figures there. Question on that there? Yeah, so how I would put it in is I would roll 6.49. I would hit your exponent button. I would hit your negative button, and then 7. And then really you're multiplying by 1, so you don't really need to do that. And then you're going to hit your divide button to divide by what's on the bottom. And in this case, depending on your calculator, but to be safe, you probably would just hit 1, your exponent button, your negative button, and 9. Yeah, and then hit equals. Yeah. And then you should be in business at that point. Again, if you do have one of those calculators with the wheel and the times 10 one, you got to put parentheses around the numbers like we talked about. So if you have one of those calculators, you got to do that. Other questions on that there? Now, sometimes people want to convert from like one prefix to the next. And, you know, there is like a song. Yes. I'm going to say maybe, but maybe not. It will probably show up, I think. So I think it will show up. You need to know how to use it correctly. Yeah. It will show up maybe like, you know, like we just saw there, kilos 10 to the 3 or something like that. So you need to be able to use it correctly that way. Yeah. Question? You will get a periodic table if you need it. So you'll probably need it. So it'll be provided for you. Yeah. Other questions? So a reminder, you are responsible though for formulas and stuff like that. So you do need to know formulas as we go through it. So another thing, since we're talking kind of about prefixes and doing conversions between prefixes, is sometimes people want to convert from one prefix to the next. And there is kind of a song, I think you could do that. I don't know the song, nor do you want to hear me sing or anything, I'm sure. But let's just say, for example, we were going from I don't know, we'll do, let's say we're going to go from 4,325 centigrams, and we want to go to say kilograms, right? So that's kind of like a prefix to prefix move, right? So we're converting from one prefix to the next. So sometimes people want to just move some decimal places, and my experience is most people will incorrectly move decimal places and not end up with the right sort of answer. So it's really important just to kind of do it as a conversion problem. And what you really want to do is, in a lot of cases, is take it from the first prefix unit to the base unit, and then go from the base unit to the next prefix unit. The reason you would want to do that is you probably would have access to a table like this that would allow you to easily find those conversions and go from one to the next. So if we were to do this sort of correctly, we would first want to go from centigrams to grams. And once again, we could look at our table and find centi, which I think I circled, which is this guy, which is 10 to the minus 2. And once again, we would know that that means in 1 centigram, there would be 10 to the minus 2 grams. So again, that is the proper way to use that number. Now that I'm at grams, I technically would have to go from grams to kilograms, right? And I can now easily find that conversion by going back to the table and finding my kilo, which I think I passed on this page. So I can very easily find my kilo, which would be 10 to the 3. And now I could go, I know in 1 kilogram, there is 10 to the 3 grams. So these are very easily found conversions by not trying to go like from one prefix to the next, but just taking it back to the base unit and going from the base unit to the next prefix. In each of these cases, we could write two conversion factors. We could say 1 centigram over 10 to the minus 2 grams, or 10 to the minus 2 grams over 1 centigram. We also could do 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over 1 kilogram. So each of these equalities generated two conversion factors that we could use. We obviously are not going to use them all. We're just going to use the ones that we would need in this case. So if we were to do this here, the actual calculation, we would start with our made up number and hope for the best, 4,325 centigrams. I want to go from centigrams to grams. Which one of the conversion factors up on top should I use? The one on the left or the one on the right? I should use the one on the right, because what I can see by setting it up this way, the centigrams are up on top. So to get rid of them, I got to put the centigrams on the bottom. And that would be that there is 1 centigram is 10 to the minus 2 grams. If I stop the calculation right at this point, I have centigrams again, technically up on top, yeah, and on the bottom, and they would cancel, which means the units I'm left with, if I stopped right at this point, are what units? Grams. And where are those grams located? On the top. That means I now need to go from grams to kilograms. So because I set it up this way to make my life easier, I should now know that grams should end up where in my conversion. I should use the one on the left, because the grams are in the opposite location. Now I could take the 10 to the 3 grams on the bottom is 1 kilogram up on top. Now I know the grams will divide out the grams. The only unit left at this point is kilograms, and it's on top, which is what I want. So math-wise, I'm going to do this. I'm going to take 4,325. I'm going to multiply it by basically 1 times 10 to the minus 2. So you want to put that into your calculator using your exponent button. Now at this point, that's all the numbers are going to multiply up on top. Good practice is to actually hit equals. Yes. I'm now going to come back and divide by the numbers on the bottom. I have 1, which I don't really need to divide by, but I do need to divide by that number, which is really 1,000, or 1 times 10 to the 3, if you want to put it into your calculator that way. So I'm going to hit the divide button and divide by 1 times 10 to the 3 in this case. And I will end up with 0.04325 kilograms in this case. Any questions on that there? The answer that I got has how many significant figures? It has 4. Is that the right number of significant figures in this case? It is, because when we look at this calculation, the 1 kilogram 10 to 3 grams, that is a metric to metric exact number. Don't have to worry about it. When I look at the 10 to the minus 2 grams to 1 centigram, that also is a metric to metric exact number. Do not have to worry about it. Again, as I mentioned earlier, leaves us pretty much the original number, right? And the original number has 4 significant figures. Our answer has 4 significant figures, and we're good. Yeah. Any questions on that? I highly, highly recommend that if you're doing some type of conversion problem where you're going from one prefix to the next, even if you know that song I'm talking about or know how to move your decimal places, you got to show your work, and I would show your work and do it this way so you don't screw it up. Yes, it is very common. People screw it up all the time. Yes. I'm sorry, say it one more time. Exactly. So basically, if we just look at this, let me just do it this way. Let me find somewhere to scribble-ish. So basically what we did in that was we started with centigrams, I believe, right? And unit-wise, what we have is basically up on top, we have centigrams, right? Then we went to grams, and then we went to kilograms. So those are all the units that are up on top, right? On the bottom, we had centigrams and grams, and then we had grams, right? So just dividing like we would divide numbers, we basically are dividing centigrams by centigrams, so they're gone, it equals 1. We got grams divided by grams, which equals 1. The only unit that's left over up on top is kilograms. And that's typically what you want if you are solving for something that has just one unit like this, kilograms. You want that unit to end up on top, yeah? Now you could solve for something that has 2 units, like if you did miles per hour, like you're driving, and you want to know how many, say, kilometers per second that would be. Then you would want 2 units to stay, and you would want them to stay in the proper location, one on top and one on the bottom. And you could do this by just thinking of them as 2 separate problems, taking miles to kilometers, just keeping it all on top, and taking hours to seconds, you know, as you go through that as well. Is there another question? Yeah, you're welcome. Yeah, so in a lot of cases, these sort of conversion or dimensional analysis problems may not involve, you know, going from like one prefix to the next, if that's sort of what you're asking. But you may have to use it along the way. So for example, you may also have to go from, say, like a metric unit to like an English unit. So maybe you had, you know, that many centigrams that you want to know how many pounds that was or something like that. So in that case, you would be going from one to the next, and you would you know, follow those units. So it's not always going to be, if your question, like you're always, all you do is convert prefixes to prefixes. Not always. You may use them along the way. So for example, that one I just did there, let's find somewhere to write. Let's say we did that 4,325 centigrams, and we did want to know maybe how many pounds that was, right? So a quality that would be helpful to us would be, we would look at a table and find 1 pound is 453.6 grams is basically the conversion factor. Some books, in your book, may around 454 grams, so we could use either number, but a lot of books are around nowadays to that number. And then we also would want to figure out a way to get to pounds, right? And obviously grams are involved. So here we would want to still kind of do our first step there, which would be take it from centigrams to grams, and then we could go from grams to pounds to do that. So we would use our same centi conversion, where 1 centigram would be 10 to the minus 2 grams. So in this case, if we did this problem here, 4,325 centigrams, we would start it very similar. We want to get rid of centigrams to get us to grams, so we could then take it to pounds, basically. So we would put our centigrams in the opposite location like we did. And once again, if we did stop right here, these guys are going to cancel each other out, right? And we would be left with grams in terms of our units. And again, the benefit of doing it this way, and the way you should do it is this way, you could again clearly see that the grams are up on top. And again, that's going to help you figure out where you should put the grams using your conversion factor to continue on with the calculation. So even without writing the conversion factors, as long as I know my equality here, the grams should end up where now? Again, it should end up on the bottom. In this case, it's going to be, we'll just use this number. We'll use the 454 number. Grams is 1 pound, right? Now, again, the grams and the grams are basically going to divide themselves out. We are left with, in this case, pounds up on top, which is the unit we're actually looking for in this particular case. And we would 4325 times our 1 times 10 to the minus 2. I would hit equals. That is basically multiplying everything that's up on top. I would hit equals. Now we're going to come back and divide by what's on the bottom. In case there's really only one number on the bottom there that we're going to divide by. We'll divide it by the 454. And that would give us a number on our calculator after we hit equals of 0.95264,317. That is all the numbers, and I hope you know that you shouldn't write all those numbers. So let's talk a little bit about the exact numbers in a situation like this. So technically speaking, 454 grams to pounds, that is an English to metric conversion we just did right there, basically, right? And those are really the conversions where they're not considered an exact number. Now, mind you, if you use the 453.6, that actually would be an exact number, but a lot of books don't use that, so they use 454. So technically speaking, the 1 pound over 454 grams is not an exact number, or it is an exact number. I'm sorry, let me spit that right. It is not an exact number because it is a metric to English conversion, which means technically we should look at it. We should not look at the one part of the number, but we should look at this number the way we wrote it. And that number has how many significant figures? 3. Now, when we look at the conversion to the left of it, this is still an exact number in this case, right? And that's because it's metric to metric, so we don't have to worry about that one. And now we look at the first number, which has how many significant figures in this case? Has 4. So really, technically speaking, our answer should have how many significant figures? It actually should have 3 based off of that metric to English conversion that has actually only 3 in this case. And that would take us to 0.0953 pounds would be our right answer. And again, it's really because here I use the 454 numbers. Some people, like I said, would argue, and rightfully so, if you actually use that number, it would actually be an exact conversion, like 1 inch is 2.54 centimeters. So there is a rare occasion where, you know, you will come across that conversion factor that technically is a metric to English sort of conversion, and you really should still look at it. And that's what I meant when I said you wouldn't look at the one part of that conversion, but you would look at the part that has an actual number and count those sig figs. Again, I would say in most cases, you know, you might not come across a ton of those, but you should definitely look at those as well. Any questions on that there? All right, I clearly took a giant tangent here on these questions here, but it's kind of what's coming up. All right, any questions on sort of that? We sort of jumped into dimensional analysis and doing calculations here. Any questions on that so far here? All right. All right. So here's some of our conversions here. So we'll take a look at some of these. 1,000 meters is 1 kilometer, right? 1,000 is a kilo. So again, kilo is 10 to the 3, which if you turn that into a non-scientific notation number, that is 1,000, basically 1 times 10 to the 3. That basically means you're going to go 1, 2, 3 places and add some zeros in there. So that's where the 1,000 comes from in this case. 1 times 10 to the 6 minus 6 grams is a micro, and that's basically on that chart as 10 to the minus 6, which is the same thing as a micro gram. I think your book uses a weird symbol for micrograms, but most people for micrograms use this symbol. That's a microgram. It's kind of thing, kind of looks like a U, is usually what most people use for a microgram. 0.1 liters is 1 deciliter, and that would be deci in that case. And that is 10 to the minus 1, basically, is what that is. But again, in sort of each of these cases, this would be kilometers. This would be, I guess I'll use what it looks like in your book there, micrograms. And this is deciliters. Once again, not pull from that table is how much there is in the base unit for each of these guys to one of the prefix units. So that's really important. Up there. All right. So here again is some of our length equalities. And again, from any of these, we can write 2 conversion factors that we could use in calculations. Here's some very common volume ones. 1 liter is 1,000 milliliters. That is something that we do use a lot, and it's something you really should know. It does come up a lot. And once again, it's very common. People will reverse that incorrectly and go, there's like 1,000 liters in a milliliter. So, you know, be careful of those things. Milli is actually 10 to the minus 3, right? And so you want to make sure you do that conversion. It's basically 3 decimal places one way or the other. We talked about it, I think, as well, but these are all volumes. A cubic centimeter is a volume, and that is a volume that is reached by taking like the length times the width times the height. And if you measure each of these things in like a cube and a length measurement, and you multiply them together, that does give you cubic centimeters, which is a volume. Each of those individual length measurements here are length measurements. If you take 3 length measurements and you basically multiply them together, you get this guy, which is a volume measurement. One relationship that's really important is 1 milliliter is the same as 1 cubic centimeter. And that is the same, once again, as 1 cc, which is also a cubic centimeter as well. All right. So we took a tangent, but we actually did a lot of the slides coming up and some of our examples here. So we will lay it up there for today.